We have Dr. Dave Taylor with us tonight. He's a geologist and paleontologist, having appointments with the Portland State University and the University of Oregon. He also is affiliated with Northwest Museum of Natural History, and since receiving a master's at Portland State University and a PhD in paleontology at UC Berkeley, he's published 45 papers, mostly on marine invertebrates that lived 150 to 200 million years ago. Dr. Taylor, thanks for being with us.
It's a pleasure having you.
Thank you, Dennis. I appreciate that. So I guess, well, I'll go to share screen when I actually start the slideshow then, right? I'm going to go to share screen now. How's that?
Yeah.
Okay. Okay. And you can see the little caption of me off to the side, right? Good. Okay. So what I wanted to do this evening is, the focus of the evening is talking about what it's like to look for and to find dinosaur material. So so many years ago, I took this, there was this international conference in 1986, and I led these people from these researchers from various places in the world to Eastern Oregon and down in Nevada, Northern California, to look at Upper Triassic and Lower Jurassic rocks, because that's one of my specialties. And so there it was just a hop and skip and a jump to the Badlands in Wyoming to look for dinosaurs. So I took that opportunity after dropping my last colleague off back in Salt Lake City in Utah. So we're going to talk about looking for dinosaurs in Wyoming, and then a break in the middle is that since I work with little coiled cephalopod things that are called ammonites. I don't know if you can see that. I'm an ammonite worker, among other things. And so I'm going to talk about ammonites at the Triassic Jurassic boundary, a project in which I've been working, and then finish off with a finding and excavation of Oregon's first dinosaur fossil, the Sacrum from Cape Sebastian on the Southwest Oregon coast. So here we are, starting out, and so we're talking about dinosaurs. If I'm talking to a young school group, you can see that's the skull of a Tyrannosaurus Rex, I think from Alberta, but I just happen to have a fiberglass cast of part of the nose to one of these T-Rexes. You can see on the small screen here. And this fiberglass cast, the way it was found, there's an interesting story behind that. Down at University at LACM, Los Angeles County Museum, somebody donated $1 million to LACM to go, had them find a Tyrannosaurus Rex skeleton. So the paleontologists were laughing all the way to the bank because they know they weren't just going to find a T-Rex, but lo and behold, and they thought they were going to drink a lot of beer in the process of doing this. And so the first year, they actually did find a T-Rex, and that fiberglass piece of that skull that I showed you just now on the side screen was the biggest piece. So they had the whole skull. It was the biggest skull that had ever been found to date of a T-Rex. And it was kind of smashed on a rock and in pieces, and subsequently they prepared it and put it back together and made the whole skull. But that was the first and biggest piece that they had prepared, and a colleague of mine who was working at LACM, gave that to me. So I'll use that in school presentations for kids. So let's go on to, okay. So where I would like to take you is, first stop would be, can you see my arrow, the cursor on the screen right there in the southeastern part of Wyoming right there?
Yeah.
Okay, that's down to a place called Medicine Bow. And this is a place where the first major discovery of dinosaur skeletons in the world was ever made in 1875. So we're going to look there for a little bit. And then the second place we're going to go is the far eastern part of Wyoming to the north in Carbon County near a town called Lusk, Wyoming, into the Upper Cretaceous and look for T-Rex and other such dinosaurs there. Okay, so the first slide, and this place in south, at Medicine Bow, this is Medicine Bow. The rocks near here are from what's called the Morrison Formation. It's an Upper Jurassic formation. It's about 145 million years old. And so behind us, to the right and behind us, is Coma Bluff, and it stretches from west to east over a distance of about 6 or 7 miles. And again, just to repeat, that was the place where the first major discovery of dinosaurs in the world was ever made. So Medicine Bow was quite a bustling place in 1875 with all the mining going on, coal mining and other types of mining in the area. It's quieted down in more recent years with the loss of some of the mining, but this is the famous Virginia Hotel in the middle of town. And the town is small enough now that you're looking both in and out of town at the same time. So this is what Medicine Bow looks like today, but 145 million years ago, Medicine Bow, the main street would have looked more like this. So this is an old rendition of what these Upper Jurassic dinosaurs look like. And here's the Stegosaurus in the foreground, Allosaurus just above the Stegosaurus, which is to be the great granddaddy to Tyrannosaurus Rex. All those big meat eaters looked about the same. And then off to the right, we see the Brontosaurus or a Natosaurus looking dinosaur. And they felt, the workers at that time knew that these were sluggish, cold-blooded, dull critters, and they thought that this Apatosaurus or whatever was so massive that they probably couldn't walk on land, but it wouldn't make a very good picture to show them underwater, so they had to have them standing next to a lake. So at any rate, in the Upper Jurassic, this is what the community of dinosaurs looked like at that time. Another interesting thing about the landscape, of course, I'm sure all of you know, is that there weren't any flowering plants yet in the upper part of the Jurassic. So they were all ferns and cycads, related types of plants, and then the uplands, gymnosperms. So a quote unquote, kind of primitive and tropical looking landscape. So here's our picture. Here's Coma Bluff. Again, Medicine Bow is to our right and behind us. And in 1875, there was a railroad that went all the way down to Coma Bluff, ran against Coma Bluff, and then went on down to Sundance. This place right here in Coma Bluff was called Robber's Roost because when the train went by, that was a favorite place for robbers to go out and rob the train. A couple of railroad workers one time thought they would climb up on those bluffs there, and they looked up there and they found these great big huge pieces of stone, and they actually looked like bone. And so they got really excited because they knew there were 2 famous paleontologists at the time, Othniel Marsh, whose uncle George Peabody started the Peabody Museum back at Yale. And then there was Edward Drinker Cope, who worked out of the Philadelphia Academy of Sciences. And they were going at each other tooth and nail.
They're enemies.
They were enemies. They were trying to outdo one another, and being able to describe the biggest and best of everything. So when these workers found these bones, they got really excited. They thought, well, we're going to make a lot more money digging bones for one of these guys than working on the railroad. So they went and they got a crate of fossils, got it down to Sundance or Laramie, I think, and from there, they shipped it off to Marsh. They decided they were going to choose Marsh on this endeavor. And so they went back to the Peabody Museum. The crate sat there for some time, and then finally Marsh looked at it, and then he got really excited. And he sent them these guys wanted to work in secrecy. They didn't want Cope to know what was going on. So they sent their first letter to Marsh under fictitious names. So when Marsh got excited, he wanted to hire these guys. He wrote checks to them, but then they were to the fictitious people. They had to iron that out. Once they got that sorted out, these workers started working for Marsh, and then they started working all along the bluff. And the bones, I might mention, are so common that at one place a sheep herder picked bones off the ground and made this cabin made entirely out of dinosaur bones. So it's a dubious distinction. And Ripley's, believe it or not, is the only house made entirely of dinosaur bones. And if you're driving along the highway, you can see that. So, but I want to take you to the place where the first Stegosaurus was found. And that was actually back right up. Can you see my arrow there on the screen?
Mm.
Okay, right up in Robbers Roost area in the western end of the bluff. There's Medicine Bow in the background, right back there. So I'd take my car along the highway and then drive up to that little pond right up in here. And then I walked up through here, and there were some rattlesnakes. Walked up into there. And this pit right here doesn't look like much today, but remember, they dug there in 1877. And this shallow depression was once 80 feet long and got up to 40 feet deep. And the beds are dipping about 45 degrees. And that's why they had to dig down so far. This is all kind of soft siltstone and mudstone that's weathers off to clay. So that mound to the left of this pit is actually the refuse pile from the site. And there was a guy by the name of Arthur Lakes who started working for Marsh as well. And he was a professor. He was the first geology professor in Colorado. But he liked making watercolors and pictures of the sites, which turned out to be really valuable. But the railroad workers didn't like that at all. They thought that Arthur Lakes was just wasting his time. So Marsh got the two groups separated. They sent the railroad workers out to the east side of the bluff and let Arthur Lakes in the west side dig up the Stegosaurus. And so this is a picture of him digging up the Stegosaurus, his own watercolor, self-portrait. And he would write to Marsh and apologize because he was having to hold a lantern in one hand. This is high plains too. This is 7,000 feet in elevation. And it gets it's wet down there at the bottom of the pit, and it's cold and windy most of the time. He was having to hold a lantern with one hand and dig bones with another. So they were coming out in pieces, and he was apologizing to Marsh. Another problem is that he wrote to Marsh saying, look, this wall is caving in. It's dangerous. I want to stop. And Marsh said, no, keep going. I want all of this specimen. And so he dug and dug and dug and got everything but the last part of the tail with the spikes on it. And then the whole north wall caved in. So if anybody wants to, so they got all of the skeleton except for the end of the tail. So if anybody wants to find the end of a tail to the Stegosaurus, you know where you can go. So, and then I looked around there in the same year and went farther to got permission from the rancher who owned the part of the bluff and worked bluff and found some sauropod bones up there. It was fun to find them. And there was another group, I think from Yale at the time, that they had found the tail end of a sauropod when I was there as well. Okay, so that was from the first year that I went out there. And then on the second year I went out there, I had a class from PSU, and the group that I had with me, we ended up seeing a lot of the monuments in the area, and one guy was complaining because we got to the monuments when it was just about sundown, but it turns out he got some really good pictures. This is of the Devil's Tower, and this is going from the Jurassic area, and we're heading off further. We're heading east to the Upper Cretaceous. So if I show this picture to a college class, I'll ask them what this is, and most of them won't know. If I show it to a group of second graders, they'll say right away, well, it's a volcano. They all know for some reason, maybe because the rock's red, and they think a lot of them. So the second area, again, is in the far eastern part of Wyoming. Further east, there was ocean, but these are land deposits, uppermost Cretaceous, restricting in age. And that's a channel sandstone up there. So these are sandstones right here. So the formation is all flat lying and made up of alternating sandstones and siltstones. By that time, the Upper Cretaceous, the floral landscape has changed entirely. And I mean, we don't see all the ferns and cycads as much anymore, but you see all the flowering plants from the mid to late Cretaceous just took over the world from a floristic standpoint. So we had magnolias and willows and many of the common genera that we see today. And in the coastal areas in Wyoming, we would have seen ball cypress swamps, just like we see in this ball cypress swamp in Florida today. The only difference is that 65 million years ago, those swamps probably had duckbill dinosaurs rummaging around in them. And duckbill dinosaurs, as it turns out, probably were well adapted to a watery type environment. Of all the dinosaur fossils that we find in marine, all dinosaurs by definition lived on land. So most of the dinosaurs that we find in marine deposits, most of them are duckbill dinosaurs. So they probably, that says two things. One is that the duckbills were probably fairly common to begin with, which I think they were. And they probably liked watery environments and probably lived adjacent to streams and the ocean and that sort of thing. Here's another duckbill dinosaur that obviously is well camouflaged, and he's probably hiding out from T-Rex and holding very still at this time. So this is part of the Upper Cretaceous assemblage of dinosaurs, its own community, totally different than the Upper Jurassic assemblage. But this Upper Cretaceous includes duckbill dinosaurs, Triceratops. Has anybody seen this one before? This is from the prehistoric gardens down on the Southwest Oregon coast. I fondly call them spikes. So this is their life-size rendition of a Triceratops. So Triceratops was also common in the uppermost part of the Cretaceous. And this is another old rendition of a Triceratops. And again, you can see, again, back when this was painted in the 30s or whenever, they thought that these were lizard-like animals. So like lizards, not only were they obviously cold-blooded, they had their arms stuck way out to the side like lizards would. But we have come to realize that many of the dinosaurs, if not, were warm-blooded or at least lukewarm. And they probably had much better posture than the earlier workers thought. And when they recently have reassembled Triceratops, they have the front limbs, for example, like pillars, sticking straight down to the ground without the elbow going out. And so they were probably partly warm-blooded as well. So they're duckbills, Triceratops or Ankylosaurus, Pachycephalosaurus, and of course Tyrannosaurus Rex. And these T-Rexes are rightfully concerned because at the very end of the Cretaceous, a meteorite about 6 miles in diameter hit the Yucatan Peninsula, and it was hypothesized. One of my advisors at Berkeley was Walter Alvarez, and he came from Lamont Laboratories, and you know, came from a think tank, and he and his father made and so Walter was new to Berkeley and I was a student there at the same time. So he came on when I was there. And so he and his father made a stratigraphic section of rocks in the uppermost Cretaceous rocks in Gubbio, Italy. And they found a little clay layer at the boundary between the Cretaceous and the Tertiary. In that clay layer, they found high concentrations of iridium. And they thought, well, these concentrations are too high for iridium to have a terrestrial source here. So they figured it came from a meteorite. And they looked at other sections, and subsequently people looked at other sections around the world and found iridium. But what was interesting is that us paleontologists at Berkeley were still really totally convinced that everything happened pretty slowly and pretty gradualistically. And so here Walter comes in from Lamont Laboratory, and within a year tells all his paleontologists that no, these dinosaurs died out overnight. And so everybody in the department was in an uproar, you know. So, and of course the debate goes on today in a slightly modified fashion. And the modification is that, yeah, there was this big meteorite that may have killed off these Cretaceous dinosaurs, but every major extinction event in the last 400 million years or so is also associated with a massive outpouring of lavas. Mm-hmm. It's the same with this one here. And so probably the prevailing view is that the extinction was caused by a massive emissions of volatiles from the outpourings of lavas at the time. But who knows? Both the meteorite and the lavas may have played complementary roles, because in this case, the meteorite and the lavas happened just about at the same time. So anyway, I was on looking for dinosaurs, and this is I came upon a Triceratops skull, but it was about 40 years too late. Mm. So you can see on the right side here, here's part of the shield that's still intact. The brain case is right up in there. And then I have the horn, the nose horn I thought I found, and just propped it up there just for scale. But all of these little bits dribbling down the slope are pieces of the shield. Well, you know, you've heard that paleontologists like to work with jigsaw puzzles, but this one was a little too difficult for me. So I left it where it was and went on searching for more dinosaur material. And I walked miles off into the country, looking everywhere and covering a lot of territory. This first year I was on my own. But if you do want to find a dinosaur, it's better to find one close to the road. And so that's what I did. So that's my car right there, a Bronco. And I walked along this slope and started finding little chips of bone, no bigger than the end of my finger, each little chip, but it was over a distance of about 15 feet. And I thought, oh my goodness, there's a skeleton under there. And so I started digging in, and that's where I found vertebra. And I realized it was a Triceratops when I found this bone down here in the lower right, which is the upper arm bone. This is stout, short, highly curved, and then the two short lower leg bones to the left. I realized then it was a Triceratops. And then the bones, as many as 5 ribs piled on top of one another. There's probably about 2/3 of a skeleton there. And the bones they may look solid on the outside, but they're like sawdust on the inside. This is really soft rock. It hasn't been altered all that much, but just decayed. And so you have to do a really good job of putting plaster of Paris on these bones. And you have to get plaster not only around the side, but wrap it underneath, or the bottom could fall off before you roll the cast over. I also got kind of a bad reputation at the neighboring town because I would go into town and ask for cases of toilet paper. So you probably thought I had problems. So here it is. This is the the lower left is the upper arm, shoulder bone and two lower bones all plastered together, and then standing up is one of the femora. So the lower part is the knee joint, and the upper part is the hip joint up there. And it's about 4 feet high. So when I was out there on my own, between working on upper Jurassic dinosaurs and this Cretaceous one, it was a lot of hard work and a lot of walking and carrying a lot of things. So I lost 15 pounds that first year. So if you ever want to go on a diet, you just go look for dinosaurs on your own. But the second year I got smart. I took a group out there with me, a class, the PSU class. And this guy was really interested in digging up the rest of the back end of that Cretaceous dinosaur. And he moved most of this pile of dirt himself. And unfortunately, I gained my 15 pounds back when I drank beer while they did all the work. So here we are at the site. We have a string there, shows we had a grid system, map all these bones in. You can see, for example, here's in the middle of the photograph, the second thigh bone. On the left is the knee joint, on the right is the hip joint. And of course, you see me standing there on the right, so you know that I was the leader of the dig. However, it was a small dig, and I was also the water boy. I'm coming up behind there. So, and this is another guy after standing on that femur after we put a plaster jacket on it. I had a family from Eugene helping us. They were working at excavating the back end of another Triceratops just a couple hundred yards away. And then a little further away yet, we found a skull to a Triceratops. So here's the shield on the left side, a horn sticking up to the right, and the nose was gone on this one. And but there was a part of a juvenile skull right in front of the adult skull. And here we are. It's the left side of the skull. The shield is on the right. You can see the horn on the left with the nose gone. The left side of the skull is preserved, but the right side was weathered away before the next layer of rock sediment was deposited on top of it. And again, the bone's so delicate, we had to plaster well underneath, plaster about 80 or 90% of it before we dared roll it over. But there it is rolled over. And the rancher on whose land we were working was nice enough to take his pickup, bring it to the site, and haul that big heavy skull out for us. So after we were all done with that site, I took all the bones down to the Safeway store in Lusk, Wyoming, and the manager of the trucking division in Clackamas County drove the truck all the way out to Wyoming, and he filled the first half of it with our dinosaur bones. Then he drove it to Denver and filled the second half up with dog food, and then drove the truck back to Clackamas and waited for us to ride back in Portland. We were going to have a media event with Safeway stores and PSU and our nonprofit organization, Northwest Museum of Natural History Association at PSU. And we were worried we might just get the dog food back, but we actually got the dinosaur. So, and then again, this is part of our crew. This is toward the end of the trip. They call it Dr. Day's Traveling Dinosaur Show. We covered a lot of national monuments. And so, but if we get this, is much of the dinosaur right now is in a lab down in at OMSI. Again, we have about 2/3 of the skeleton. If we get it all put together at some point, it could look like this Triceratops here. And even this one, this is about 2/3 of a skeleton. You can see the lighter gray of the skull is all fabricated, and then the real bone is more, it has more of an orange cast to it. So anyway, that's what it's like to go look for and find and excavate a dinosaur. So I'm going to take a little bit of a break here if anybody wants to ask any questions at this point, or I'll just keep going. So shall I just keep going? Okay.
There's a question from Charlie. He said, did any group scan a T-Rex skeleton? And if so, can GSOC or anyone else get a copy of this laser scan file?
If anybody scanned a T-Rex skeleton, I'm not sure about that. I don't know. I absolutely don't know. You mean whether they've actually taken a laser scan and reproduced the bones out of it, like from a printing device, that sort of thing? I don't know.
Charlie, if you want to unmute and clarify your question there.
It would be a wonderful way of sharing files, because if you get a nice scan and you pass it around, other people and other schools and students can look at it, assemble it themselves, or other things like that.
Oh, you mean scan it just like photographing it then, or?
You know, well, you scan it, but it's like a 3D scan.
Oh, okay.
Mhm.
Okay. Yeah, I mean, some places do that for some of the files. You know, you can go into, you can look at certain museum catalogs, and some materials photographed or scanned or even 3D scanned, and others aren't yet. So I guess we'd call it a work in progress. How's that?
Yeah.
Yeah.
Okay. Well, we have a favorite animal mascot for GSOC. It's the Mylogalus hatcheri.
Oh,
Gopher.
oh, cool.
And so if we get a 3D scan file of it, there's some people will be very happy.
Oh, okay.
But that's the sum of it. Other people may want duck-billed platypuses or duck-billed dinosaurs, excuse me.
They might want that. Who knows? Yeah, everybody with their own preference, right? So,
Yeah.
but that looks like a cool animal right there. So,
Oh, it is.
yeah, no, it is. So,
But we're trying to find someone who has a 3D scan file that we can then get off of them.
okay. Well,
That's
I'm
the hard
not
part.
technologically astute enough to be able to do that myself. So, but that's a worthwhile thing. That'd be a good thing to do. That'd be cool. Very neat.
Thank you.
Sure. Well, should I keep going?
We have another question from
We
Denny
have-
Chamberlain.
Yeah, we have a question. Yeah.
Carol, you want to read that?
Yeah, what is the process for casing and plaster? What keeps the plaster from just sliding off?
Oh, okay. Yeah. So what you do, so you uncover the bone and then you solidify it. You put glues on it. So, you know, people used to use shellac, and now they have fancier glues that they use now. I won't get into that, but most of the fancier glues today are soluble in acetone. So you saturate the
PDA.
bone with glue to solidify it.
Mhm.
Then after that's dried, then you put layers of wetted tissue paper and put toilet paper and coat the bone with that. So that, and you do that so that when you put the plaster on, it doesn't stick straight to the bone. So, okay, so solidify the bone, put paper, wetted tissue paper on it, and then you take burlap and burlap strips and put those in plaster, and then put burlap soaked plaster in very few layers covering the entire bone, and it makes a hard cast, just like the cast the doctor would put on your for a broken arm. So the burlap provides the fabric for holding the plaster together. Does that make sense?
Yeah.
Okay.
Thank you.
Okay, I'll go ahead and continue then.
Yeah, go ahead.
Okay, so this is a bit of a diversion here, but so in this, so we looked at Upper Jurassic, about 100 and the rocks in the Morrison Formation, 145 million years ago. The Cretaceous, that was about 65 million years old. And then another time period that I have personally studied quite a bit is the Triassic-Jurassic boundary, which is right at about 200 million years. And so that's a major extinction event. That's a time when, for example, the Ammonites almost became extinct. Only one form or at the most made it through. And then after the extinction event, they rediversified again. And a lot of other animals were decimated at the end of the Triassic as well. And so the prevailing hypothesis is that there was a major area of volcanism called the camp volcanism. And you can see this is a picture of all the continents when they were still glued together. You can see where South America and Africa are glued together, North America and Europe. And the camp volcanics are in this large red area. And these were, massive basaltic extrusions and intrusions of lava over a relatively short period of time, and they probably caused the extinction event. And so again, the fossils that I work with, or that I know most about, are ammonites. They're a squid-like animal that grew a shell on its back. They appeared 350 million years ago. And they're, kind of related to the squid. The inner whorls of the shell were air-filled, and so they were like little miniature submarines that would swim around in the ocean. They evolved rather quickly, and so animals that evolve rather quickly are susceptible to extinction. That's why they became almost extinct at the end of the Triassic, for example, and then finally died out the same time that dinosaurs did at the end of the Cretaceous. So this is getting a little technical. I don't want to get into it too much, but ammonites tended to do the same thing over and over and over again. And we'll pretend that this line right up near the top of the screen right here, can you see the arrow running across the page?
Yes.
Okay. We'll pretend that's the Triassic Jurassic boundary right there. Okay. So what happens, we'll jump back down to the bottom of the screen, and when a family of ammonites first appears, it'll tend to look like this one at the bottom of the screen. It'll be evolute, highly coiled, relatively smooth. And then as it evolves, it diversifies into a whole suite of ammonites that have strong ribs, hooks, bumps, and knobs on them, a great variety of forms. But then in the case of the upper Triassic, if you look at these pictures close to the top, most of the ammonites, this is kind of bizarre again, in the last 2 or 3 million years, all those ornate forms in the last 2 or 3 million years of the Triassic dropped out, and you get a bunch of smoothies at the top of the Triassic. And you get all smooth ammonites, and then you get a few of the first appearance of what you call heteromorph ammonites. Has anybody heard of those? They're kinds of ammonites that became uncoiled. So bizarre looking little ammonites. So there was this funny assemblage of ammonites in the last 2 or 3 million years at the end of the Triassic. And then bam, there was a Triassic extinction event. And then one of these ammonites evolved very quickly back into a generalized small evolute form again. And then after the extinction event, the ammonites, since they made it through at least by one form, they started diversifying into a whole array of things again. So the ammonites went through the cyclical evolution kind of. Started out with a generalized smooth form, develop a whole bunch of ornate forms, have some environmental event that makes them want to almost go extinct, and then they revert back to a smooth generalized form again. And that's happened time and time again in the ammonites. And that's what happened at the Triassic-Jurassic boundary. This is near Hawthorne, Nevada, and this is the section that I studied in the Triassic-Jurassic boundary. And all the rocks at the lower part of the screen up to, there's a white band running across there. Just a few meters above the white band is the actual boundary. And then some of these white beds in here are almost barren of fossils. And then you have Jurassic fossils, whoops, typical Jurassic fossils in the upper part of the bluff. And so this is a stratigraphic section right here. We had a carbon isotope curve. And where you see the carbon isotope drops off a lot, that's where the extinction event is. All the animals from the Triassic thrived up to that point. And then from there, you got 5 meters where everything almost drops out. There's hardly any fossils, and then you start getting Jurassic forms again. So there's a lot more to it than that. But anyway, that was an interesting section to study. And I just published a couple of papers on that recently, and got more work to do. So jumping back to dinosaurs, we have this is the first dinosaur that was ever found in Oregon. Okay, this is the one from Cape Sebastian. It's the sacrum to a duck-billed dinosaur. But I wasn't the one to find this thing, to begin with. I excavated, but I didn't find it. It was a couple people from the U.S. Geological Survey. They were mapping down in Cape Sebastian, and they came across, they in the notes that they made, they figured it was dinosaur. They knew, they had an idea it was a dinosaur bone. And so the news kind of got around. Eventually everybody in the paleontologists in Oregon knew about it. Bill certainly did. And one of my first advisor down there, J. Wyatt Durham, and Don Savage and other people made a trip up there, I think in 1969, and they looked at it, and they reaffirmed that it was a dinosaur at that time. But nobody wanted to dig it out of the rock. It looked like a really hard job to do, and I was the only one stupid enough to take up the challenge, So I got a group of people, and we spent about 4 days on it. And we chiseled all the way around it, and here's a close-up working on the specimen. And as it turns out, the sandstone wasn't all quite as hard as it looked out to be. It looked like a really daunting job to begin with, but you start chiseling away on it, and that rock chipped away, and we got it out in a couple of blocks, and it was fine then. It took 4 days. So the whole thing is about 1.5 feet long, and the parts to the right, going to the right, there's more vertebrae in there. You can't see them; they're just pieces to them. But the whole length of this sacrum indicates that there were 9 fused vertebrae. This was in 1994 that we dug this up. The summer of August of 1994. And there was a Society of Vertebrate Paleontology meeting in Seattle a couple of months later, and there's a colleague of mine that took the specimen up there. But he only took the main portion. He didn't take the last few vertebrae, just the main portion up there, showing 6 of the vertebrae. And Jack Horner was up there at the time. He's the leading expert he was a leading expert on dinosaurs, especially duck-billed dinosaurs at the time. Since he only saw the first, it was obvious to him that it was a dinosaur. There's no question about that. He was just debating as to whether or not it might have been a meat-eating or a duck-billed dinosaur. Had he seen those pieces to those other vertebrae, he would have known offhand that it was a duck-billed, because it's the only thing that has 8 or 9 vertebrae. But he identified it at that time. And that's the specimen right there. It shows where it sits in the hip of the duck-bill. And there are 2 different kinds of duck-billed dinosaurs. There's the crested duck-billed dinosaurs, and then this kind, which is a non-crested one. And that's what that hip bone belonged to, is a non-crested dinosaur. So anyway, the first dinosaur, and that's the picture of it right there, one side. Now, the top side was eroded, and so here's the top side as we have it excavated, and this is the neural canal, and you can see how it's narrow. The right side is the front of the animal, and the left side is toward the back. And so you can see the neural canal is narrow in the front part and widens out dramatically toward the back of the animal. And the old timers used to think, well, you know, again, these animals are so big and so dumb, they had to have a second brain, and that's where the second brain was. But we know now that's not true. Lots of animals have an enlargement of the neural canal toward the back of the animal. So at any rate, I think that's the last slide. So again, we end with the duckbill dinosaur. And then of course, there was a report of another dinosaur find also in the Mitchell area in Eastern Oregon. So now, okay, that's it. So I guess we'll open it up to questions. How's that?
Okay, thank
Great,
you.
thank you.
Okay.
Very good. Okay, Carol, do you want to address some of the questions that came in?
Sure. Charlie was asking if there's any ammonite fossil that includes their tentacles.
I have, I've seen reports where there would be some, I haven't seen them where you have the tentacles actually preserved in outline. But I think I've seen some cases where there's some little spicules or something, lines of spicules or something indicate that tentacles were still there. So I don't know if we have direct evidence
Mhm.
to how many tentacles there were, except they're related to the squid, in which case they'd have 2 long tentacles and 8 arms and something like that.
Yeah, I was figuring that since you have impressions of the skin from other dinosaurs, maybe the impressions in the sand, in the silt or the sand from the tentacles as the ammonite died. That's,
Yeah, well, the duckbill dinosaur has lots of skin impressions on it, and the duckbill dinosaurs have lots of skin impressions. There's many examples of those, and they had this really leathery, hard, kind of little bony skin, and it does get preserved sometimes. But the ammonite parts were so soft, they usually just didn't get preserved. There is a case, I saw a publication from 1830 of a squid-like animal, a belemnite, a squid-like animal that actually had the ink sac preserved. And so this is a publication from 1830. It was by a guy by the name of Wright, and he peeled the ink from the ink sac off, put it in a jar, and reconstituted the ink, and then proceeded to write with it. So we wouldn't do the same thing today. We'd analyze the ink or whatever, you know. But there are some cases of soft part preservation, and that is, I know of that one about the ink sac being preserved. So, and it was in a clay, you know, and so there wasn't much water not much opportunity for water to seep through that.
Okay, we have a couple, let's see, we had a couple questions discussing carbon isotopes. Pretty much people agreed, talking back and forth, that carbon-14 doesn't go back nearly far enough to be of any use. Do you want to comment on that?
Well, there's carbon-14 dating. And so those are ratio of 2 different isotopes of carbon, and accurate dating for carbon may go back, what, 30 or 40,000 years or so.
Mhm.
The carbon isotope that I was talking about, and people are doing this a lot now, is that they're looking at the ratio of organic carbon to inorganic carbon. And as where the organic carbon drops out, you have a major decrease in organic carbon. That's the part of the curve that indicates an extinction event or loss of life at the time. So there are 2 different things. One is you can use carbon for ratios, isotopes for dating rocks, fairly young rocks, but then you can use the carbon isotope curve to indicate whether there was an environmental catastrophe or not. Okay.
Okay. Let's see, we had, Chris Morgante had a question about Ammonite evolution. Are you with us, Chris?
Yeah, can you hear me?
Unmute
Yes.
yourself, yeah,
Can you hear me?
go ahead.
Sure.
Yeah, just real quickly, you showed a nice sort of timeline of Ammonite evolution where it started off smooth and then it went into ornate.
Mm-hmm.
And then it transitioned back to smooth. And then, of course, you had an extinction event, and then the ones that remained were smooth again. But is there a reason why, or is there a hypothesis on why the ornate evolved back to, or if you want to use the word back to, that smooth? Or is it just we don't have enough fossils to make that kind of, see what that path is?
Yeah, well, I'll use a technical term, that transition like at the Triassic-Jurassic boundary, and it doesn't happen just at extinction events. You can get an Ammonite family evolving and they go through this trend. And in many cases, the family doesn't end up with all smooth forms, but they tend to become what you call more involute and tend to be a little bit smoother. But what happens when you have an event where it changes back to that generalized form, it's almost like there's no intermediate forms. And it's hard sometimes to find the ancestor-descendant relationships because it's what they call a saltational jump. It's very sudden in the geological record. There's probably intermediate forms somewhere, but we just don't see it. It's probably the regulatory mechanism in the genetic structure switching whole combinations of genes at the same time.
But is there a reason for it from an evolutionary standpoint? I mean, does the transition, is that adaptation beneficial in some way that seems obvious?
No, a lot of functional morphology isn't obvious, and so all that we know is that it switches back to a generalized form, and this is the form that's probably most adaptable. And since it's not specialized. So this is the hypothetical answer, is that these other late ammonites were rather specialized in one way or another. And then the transition back to the ancestor transitions, you lose all the specialized forms and you just get this rapid jump back to the infant or the juvenile form again, this more plastic, and then can evolve back into the ornate forms later in time. So, but there's we don't have, I hate to use this word, we don't have a deep understanding as to why that happens. We can make these observations, but why is still a guess, I'd say. There's a lot to learn out there,
Yeah, I can imagine. Thank you very much.
Yeah.
Okay, we had a question from Wes Mahan that wanted to know why there's the paucity of dinosaur fossils in Oregon, so different than Wyoming. Why was there only one found on the coast and one found in Central Oregon? You want to address that?
Yeah, I was going to try to come up with a funny answer, but I couldn't think of one. So. because
we were ocean then.
Yeah, we're all oceanic then. Yeah, there was I mean, okay, again, by definition, dinosaurs are lived exclusively on land. So the things like ichthyosaurs that lived in the sea and pterodactyls that flew in the air, they aren't dinosaurs. So all the dinosaurs are all strictly land-dwelling animals. And most of all the Mesozoic rocks were all marine in Oregon. Oregon in the Jurassic really wasn't even part of the continent then. There were island arcs out there. And so that's why the fossils are so rare. And this thing here, the Sacrum of this duckbill, actually came from very shallow water deposits. These were deposits that were laid down I'll get technical on this sense, for a second here in a sequence of what's called hummocky cross stratification.
Mhm.
And that means these beds were all laid down on about 50 meters or less of water. So it's a shallow water deposit anyway. So the duckbill dinosaur died close to shore or was in a stream and got washed out to a shallow sea, and we just got lucky enough to find it then. So yeah, so there's probably more dinosaurs out there somewhere. We just haven't found them yet.
Good.
A couple people were curious about your opinion about the Tanis site,
What site about that?
about the Tanis site.
Oh, I'm not familiar with that. The Tana site.
Paul, you want to clarify?
It's kind of an amazing find in North Dakota that allegedly has, it's coming back to you, right? It
Yeah.
has sturgeon with microtectites in their gills because that's
Yeah.
when the asteroid was raining down.
Right, right. You mean my interpretation of it?
Yeah, I mean, it's such an amazing story
Yeah,
that these saltwater fish were washed into freshwater streams by a sesh caused by the asteroid at
Sure.
exactly the same time that little pieces of glass were raining down from the sky.
Right, and spherules and things like that. Right. Yeah. I mean, it's a good story, right? and it's a convincing story. And I did read the article, and I did read carefully, but I just haven't thought about it again too much lately. But yeah, I mean, I think what they said is a good chance of what they said is valid. I mean, of course, as a scientist, I haven't gone back and looked at it myself, firsthand. So I don't know that it's perfect, but I think it's pretty convincing.
That's great.
Yeah.
Thanks.
A pretty cool story. And again, we still don't know ultimately what killed the dinosaurs, whether it was the magmatic work of magmas or the meteorite, or both together.
And then we did have a question about the volcanics, the Camp Volcanics. A couple of people want to know if they are related to the volcanics in Connecticut, Newark, Gettysburg, and the Triassic basins of the East Coast.
Yes, they absolutely are.
Yeah, and
So,
then
again,
somebody else thought that it was from the rifting of Pangea.
right. It was probably an initial rifting and just the beginning of the formation of the Atlantic Ocean then. So I know it's an absolutely huge area in which these volcanics were exposed.
Yeah.
And this is a side light, and I don't have it. I worked with some people in Switzerland, and one of the best labs for dating rocks is in Geneva, Switzerland. And I did a project with this Schaltiger, and when they date rocks, for people to, in most labs, say 10 years to come up with a normal date, they get a bunch of zircon crystals out of an ash bed, and they'll date them all at once and come up with 200 million years plus or minus 500,000 years. But the dates that come out of this lab in Geneva, I asked Urs, I said, well, how good is your lab? He says, well, it's one of the best labs. It was one of the 4 best labs in the world. And so the dates that they get are plus or minus 10 or 20,000 years or so. And so if you can get several dates in succession, you can come up with a really good chronology. And we got some at the Triassic Jurassic boundary. And I worked with a student from Geneva a few years ago. We published in 2019. We did this nicely formation in Eastern Oregon that covers a 3 million year span, and I did the ammonites and the stratigraphy, and he did the dates, and he got 8 radiometric dates in succession. So it makes a nice chronology that way. So
Great. Okay, any other questions?
Yeah, there's one more here that's how do you now differentiate between the organic and inorganic carbon from the Triassic?
I let the geochemist do that. It's C14 versus C13, something like that. And so that's all it is. It's a different molecular, it's a different isotope of the same element. And I don't know how they do it because I've never done that myself. So.
Well, we're at our 8:45 point. I think we'll stop the recording here.
Okay.
Do you have time
And,
one